Hello guys, welcome to this new video. So this is going to be question 8 in the May 19 time zone 1 paper 3, and it's the rigid body mechanics question from this paper. So here we're given this solid cylinder of mass m and radius r. It's free to rotate about this horizontal axis, and we have tied a rope around it with a block at the end of it that will make this cylinder spin. And we are told that the system is initially at rest, and we're also given the moment of inertia of the cylinder. So firstly, we need to show that the angular acceleration A, alpha of the cylinder, is g over 3r. So for this, we first need to notice some of the forces acting on this system. So we know that on the block there will be a weight force, and we also know that there will be a tension force in the string that's keeping the string attached to the block. And we also know that the block is going to be accelerating downwards, so that means that there's going to be a net force pointing down. And so from this we can see that the weight will be larger than the tension, as that's how it will be, so that when we add the weight and the tension we'll have a force pointing downwards. And we can also know that the tension is going to be the same everywhere along the string, as we always just assume that tension is constant throughout the string, which means that we can also draw this tension force over here if we would like. Is the same everywhere. And so from this, we see that the tension force is what's going to be providing the torque about this axis of rotation with a distance of r. So it's not going to be the weight force providing the torque, as that is not what is here by the rotation side. So it's the tension that will make the cylinder rotate, as that is in contact with the cylinder here. If there would be no net force, so if we would not be accelerating, then we could say that the weight force is providing the torque, but that's also because then the weight force would be equal to the tension force, and that's why we would have no net force. Even then the tension would be providing the torque, but then we could replace it with the weight since they're equal. But here that's not the case. Here we need to use the tension. So now we can write up some equations. We know that torque is equal to moment of inertia times angular acceleration. And well, here torque is just going to be the force, which is tension, times the distance of the axis, which is going to be r. And this will be equal to the moment of inertia times the angular acceleration. And then we can also write down the net forces acting on this system, so the equilibrium of the forces. So we can say that the weight force minus the tension will give us the net force. And well, we know that the weight is just mass times gravity, so mg over 4. Then we still have the tension. And then the net force we know is m times a, where a is the acceleration of the system. So that will be m over 4 times a, as we're considering the acceleration of the block here. And then we need one more equation, which I believe is not in the data booklet, is that a is equal to the angular acceleration times the radius of the motion. And if we think about this, it's very similar to this expression. It's just here we took the derivative of both sides with respect to time. So we know change in velocity over change in time is acceleration, and the change in angular velocity over change in time is just the angular acceleration. So it's worth remembering this relationship, but also this top one. These two are very important. And then what we need to do now is just combine these in such a way that we end up with this expression. So firstly, here we could divide both sides by r, so we get tension is equal to 1/2 mr alpha, and then we can plug in the tension and the angular acceleration over here. So we only have angular acceleration, which is what we're going to have to solve for, like this. M over 4 times alpha times r. And then we can see that the masses will all cancel out, and we can bring this over to the other side to add them. Then we'll get that g over 4 is equal to 1 over 4 alpha r plus 1 over 2 alpha r. this is just going to be 3 over 4 alpha r. And then now we need to rearrange for alpha, so we can multiply by 4, divide by 3. So we'll find that this is 1 over 3 g over r, which is what we have to show. And then now we need to show that the tension in the string is mg over 6. So we had this expression for tension already. So tension is 1/2 mr alpha. And now we know the expression for alpha, so we can just plug this in. Alpha was g over 3r. The big r's will cancel out. 1 over 2 times 1 over 3 is 1 over 6. This would be mg. So that is how we can show that. And then we are told that the block falls a distance of 0.5 meters after its release before hitting the ground. Show that the block hits the ground 0.55 seconds after the release. So what we can do is, well, we can find the acceleration of the block, as we know that the acceleration is just the angular acceleration times the radius. So here we just want to bring this problem back to a Suvat equation, the simple mechanics part. So this is not related to circular motion or rotational motion. We want to see the time fallen by this block, so we can calculate the acceleration of it, and then we can use a Suvat equation to solve it. So we know angular acceleration is g over 3r. So if we plug that in here, we'll find that the acceleration will be g over 3, which is 3.27 meters per second squared. And then we need to use this equation that the distance traveled is equal to the initial speed times time plus 1/2 at squared. We know that the initial speed was 0 as it started from rest. And so if we rearrange for t, we'll find that it's equal to the square root of 2s over a. And then if we plug everything in, 2 times 0.5 over 3.27 will give us 0.55 seconds, like this. Then we're told the radius of the cylinder and the mass of the cylinder, and we need to calculate just before it hits the ground the angular momentum. Well, if we look in our data booklet, well, first at the start we had 0 angular momentum as we started from rest. So if we calculate the change in angular momentum, that's going to be the angular momentum itself just before it hits the ground, as it started from 0, so that must be the change. And we know that the change in angular momentum is the torque times the change in time. This is very similar to the formula from mechanics that the change in momentum is force times time. It's just that instead of this we have this, and instead of torque we have the force. And well, we know how to calculate the torque, as that is just the tension times the radius and then times delta t. So the tension here is going to be, well, this 1 over 6 m times g, as that's what we had to show in part 2. So 1 over 6 m times g, like this. The radius is 0.2, and then delta t was 0.55 seconds. And then if we multiply these, we get 2.2 joule seconds. And then the last part of this question, we need to calculate the kinetic energy of it. So for kinetic energy, we have the formula that E kinetic is equal to 1/2 moment of inertia times angular speed squared. So if we could find the angular speed, then we could just plug into this formula and find the kinetic energy. And well, luckily we know the acceleration of the block and the time it took to accelerate, so we can use the equation that the final angular speed is equal to the initial plus acceleration times time, but we know it started from rest, so this is 0. So the final velocity, angular velocity, will just be the acceleration times time. So that will be, well, we know acceleration is just the angular acceleration, obviously. So this I should have written an alpha here. So the angular acceleration, as we're talking about rotational kinetic energy here, because we're talking about the cylinder, not the block itself. So the angular acceleration was g over 3r times the time. So 9.81 times 0.55 divided by 3 times 0.2. This will give us a final speed of 8.99 radians per second of the cylinder. And well, we know that E kinetic is 1/2 like this. We know the moment of inertia was given previously in the question. So that was 1/2 times mr squared times angular speed squared. So this will just be 1/4 times the mass, which is 12, times the radius squared, which is 0.2 squared, and then times the speed squared. This will give us the final answer of 9.7 joules. So this was the end of this question. I hope I was able to help with this question, and see you in the next video.